Welcome to the 11th BAA Wednesday webinar. As usual, this is being streamed via both Zoom and YouTube, with the event recorded on YouTube. Those who are attending via Zoom can submit questions using the Q&A button at the bottom of your screen. We won't interrupt the presentation to answer questions. Instead, we'll hold the Q&A at the end of the talk. In light of recent events, I would like to emphasize that the BAA is committed to creating an environment where diversity is celebrated and everyone is treated fairly. It is my pleasure to welcome this evening Professor Fraser Pearce from the University of Nottingham, who will give tonight's webinar on Adventures in the Goldilocks Zone, the search for other Earths. Professor Pearce specializes in the theory of the formation of structure in the universe. In particular, he models the evolution of clusters of galaxies using some of the world's largest parallel supercomputers. He also has interest in X-ray emission from clusters and the feedback of energy due to supernova explosions. Over to you, Fraser.
Thank you, Andy. It's a pity I can't see everybody here because we're obviously Zooming rather than having this talk in person. Before I get started, though, I think I'd take a couple of moments to echo what Andy said about diversity and reiterate that certainly we're all fully supportive of the BAA statement of their wish to support the current interest in diversity issues. Of course, within astronomy, we need to be very much aware of this. It's very clear that within the astronomical community in the United Kingdom, for instance, black researchers are massively underrepresented, and so this is the diversity issue is not something that we can just pretend doesn't exist for us, because it certainly does. I mean, the black population of the UK is somewhere between 3 and 4%, according to the ONS, and there are something like 500 professional astronomers in the United Kingdom. So the underrepresentation is very high. Black and minority ethnic make up about 14%, so 1 in 7. So we can all reflect on whether that proportion follows through into our colleagues and our own societies. Anyway, on to the subject of tonight's talk. So I'm going to talk a bit about searching for other Earths, but I'm going to start actually by talking a bit about the solar system. Let's just see if I can actually get this to work. Oh. So I'm going to start by talking a bit about the solar system. So on the top of this slide, you can see what is a more usual representation of the solar system. And so what you can see is the sun off to one side. And what's shown here are the planets with the size approximately correct. So you can see on the inner planets, there's 4 rocky planets, and then outside them, there's the 4 gas giants. And those are, of course, much bigger because their densities are much lower, and they're also more massive. So this is the ordering of the planets within the solar system, which we're all very familiar with. And what we can clearly see is that this is not random, because it'd be unlikely if these were just random that the 4 inner planets would all be rocky and the 4 outer planets would all be gaseous. And of course, there's a reason for that, and that reason is the sun. It's much hotter near the sun, and so volatiles only really start to condense and start to join into planets in the outer part of the solar system. So in the inner solar system, you get these rocky planets. On the outer solar system, you get these much bigger planets made up of largely made up of volatile materials, and that's pretty much how we thought solar systems would be. And we'll come back to that more a bit later. But that's the solar system in size. At the bottom here is the solar system in distance. So the thing to remember here is that all those rocky planets are pushed right down into the inner solar system. So this is marked out in astronomical units, which is the distance from the Earth to the Sun. And what you can see is that if the Earth is, if you think of a scale where the Earth is at 1 meter or a yard from the Sun, then Jupiter's at about 5 yards, 5 meters. Saturn's at 10, Uranus is at 20, and Neptune's at 30. So the outer bit of the solar system is much more spread out than the inner bit. The top picture is not to scale in terms of distance. And that's the solar system as we discovered it was like in school, minus Pluto, of course, for some of us. So that's the solar system as we know it. The other thing that goes into this, though, is how the solar system forms. So here is a picture, an astronomical image. It's actually a picture of T Tauri, and this is a star in the process of forming and just essentially turned on. So you've got a cloud of material which condenses into the middle as star forms. And what you can see, what's interesting from this picture, is there's lots of structure. It's not just a spherical sort of boring collapse. There's lots of stuff going on. And what we think in these early parts of stellar evolution is that essentially a disk of material, disk of debris, you can sort of see some structure that looks like this running sort of diagonally across this, and there's another one that comes across the middle. Structure forms within this stellar forming region, and this is the archetypal of what are called T Tauri stars. This is actually T Tauri itself. So that's an image. Here's some more images. So what we think happens is that near the star you end up with a thin disk, a disk of debris and material left over from the sun, the star in the middle forming, and we can actually image a lot of those disks nowadays. So this is some pictures from Alma, and what you can see is these beautiful disc-like structures. I mean, you can think of them a bit like a bicycle wheel, and some of them are face on and look like circles, and some of them are inclined relative to your line of sight, and that's why these things look like they're elliptical. These are all sort of circular in structure, a bit like this one that's on the bottom, third one down on the left, and that's face on. But these discs are not sort of boring and smooth. What you can see within them is these lanes, these bright circles and dark circles within them. And what we think's happening is that is planets forming. Those are direct evidence of planets forming within those disks. Now, of course, what we can do, what I've been particularly interested in, is modeling. You can actually build models of what's going on here, and here's two examples of those models. So these are face-on disks now of material where planets have been allowed to form within those disks. And what you can see is in both of these cases, you get planets forming. In the one on the top left, what you can see is a planet has formed within the disk, and it's sort of generated this sort of spiral structure within the disk. And if you wait a bit longer, what happens is the planets carve out these gaps in the disk, and that's a bit like what we see in, for instance, the gaps in Saturn's rings. So the objects that form end up carving out a gap, but they also leave these leading and trailing arms within the disk. And what happens is that the planets don't stay where they are within the disk. They move in and out, or inwards or outwards, depending on whether the outer arm or the inner arm pulls more or less. So generally, though, planets appear to migrate inwards towards the star within these disks, and the rate at which they migrate tends to be related to the mass of the planet, because the more massive the planet, the more angular momentum it has, and so the longer it takes to spiral into the middle. So bigger things all planets tend to spiral inwards, and they tend to, in general, go faster if they're less massive. So the more massive ones go more slowly. So that's sort of the theory of how planets form within these disks and how they move around. Why is that interesting? Well, it connects to what we think happened in the early solar system, because before we do that, I need to just have a slight diversion because it's relevant for the next bit. This is a movie. So this movie shows the Millennium Bridge, which some of you will remember. So the bridge was built across the Thames, and when it was ready, lots of people went to visit it, and it didn't stay still. It had this pretty horrible, to start with, resonance. You can see that bridge is moving backwards and forwards as the people moved across it. I'll just play that again. So they built the bridge, and as people walked across it, they tended to step in time with each other because the bridge was swaying, and that amplified the sway, and you got this really big resonance happening between the people moving. You can see them all moving in lockstep, essentially driving that oscillation of the bridge. And this is an example of resonance that happened when in bridge building, but resonance happens all over physics, and resonance is important for the next step because here's a diagram of what we think happened in the early solar system, and for this, resonance is important. So in the early solar system, we think the solar system formed something like this at the top. So you've got a big planet, Jupiter, and inside Jupiter there were lots of rocky asteroids, because, as we already spoke, inside the snow line, there are lots of rocky, that it's hard for volatiles to condense, and so you end up with lots of rock formed into objects. Once you get outside the snow line, you can form lots of volatiles, and so you condense lots of volatiles, and so you tend to form a big planet there. So Jupiter forms pretty much close to the snow line, and outside that you get some other big planets and more water-filled sort of cometary material. So you have this nice bifurcation in the solar system: rocky stuff on the inside without very much water, and then the planets with volatiles are the gas giants on the outer solar system. But then, of course, the debris disk still exists, and so what happens is that Jupiter migrates inwards, as objects do within the residual disk. It moves inwards, and it would indeed just crash into the sun eventually, and sweeping up all this stuff inside it. But in our solar system, what we think happened is that Saturn formed outside Jupiter, but because it's lighter than Jupiter, what happens is that it migrates inwards faster than Jupiter does. So it catches Jupiter up in its migration. Now, so the two objects are moving in together, but Saturn's moving in faster, catching it up. And what's interesting is that eventually it reached the point where it's in a resonance, just like the people walking across the bridge that we just saw. And in fact, we think it went into a 3-to-2 resonance. So for every 3 orbits of Jupiter, Saturn went round twice. It's further out, so it takes longer to go round. So in that 3-to-2 resonance, they just end up moving round the star in the middle in that 3-to-2 resonance. What's interesting about that is that the combination of the planets in that 3-to-2 resonance, they don't have a spiral structure between them. They basically clear out a combined lane, and that object, that resonant object, doesn't migrate inwards; it migrates outwards. So what happens is that once the resonance forms, the inner migration stops, and they start to wander back out again through the primordial solar system. So you end up with Jupiter and Saturn. Jupiter ends up essentially back where it started from. This is called the Great Tack, or the Grand Tack. So Jupiter moves in, sweeping and messing up all of the nice split between rocky objects and cometary material, messing it all around, mixing it all up, and then it comes back out until it's pretty much where it is now. And by 500,000 years, the grand tack was finished, and Jupiter was back out at pretty much where it is today. And you may wonder, of course, well, but hang on a minute, Jupiter and Saturn are not currently in a 3:2 resonance, so that doesn't sound sensible. Indeed, that's true, and that's where something called the Nice scenario comes in, because the way out of that conundrum, the fact that Saturn is not in a 3:2 resonance with Jupiter currently, is that what we think was that originally there weren't 4 gas giants, but there were in fact 5. We think there was a 5th gas giant, and that gas giant has a close encounter, probably with Saturn, as a close encounter, gets thrown out of the solar system, and in the process breaks the resonance between Jupiter and Saturn and moves Saturn to where it currently is in the solar system. So, and that's called the Nice scenario. So we think that there were originally 1 more gas giant than we currently have, and that's how we arrive at our solar system as it is now. We think that's the current view of how the solar system gets to look like it does. And you may ask, well, hang on a minute, that's quite complicated. What's the evidence for that? Why do we think that's true? Well, one of the key pieces of evidence is the Earth, and the fact that we have a lot of water on the Earth. Because, as we said at the beginning, when we looked at the solar system itself, water doesn't condense inside the snow line. There shouldn't be lots and lots of water in the inner solar system. It should look a bit like the top here, where all the inner stuff is essentially dry, and the Earth is obviously not dry. There's quite a bit of water, and one way of doing that is to have Jupiter wander around in the solar system and mess up all of these little bits of material, and bring lots of cometary stuff from the outer solar system into the inner system, which can then supply the water that eventually ends up on the Earth. Another argument for this scenario is, in fact, Mars. Mars is very light. It's only about 11% of the mass of the Earth, and you'd expect the planet in Mars's position to be a bit bigger. You tend to you have more material to start with. If you think about a disk, that it goes like the square of the radius, the area of the disk, and so there's more material to form Mars, and yet it's only 10% of the mass of the Earth. And that's a sort of surprising, and it's less surprising if you think that Jupiter wandered around through that part of the solar system, sweeping up all of or a lot of the material into itself, and so reducing the amount of material left to make Mars in the end. So the two example pieces of evidence are water in the inner solar system and the smallness of Mars, for why a scenario like this might work for how the solar system formed. So there we go. That's our solar system. Now, exoplanets, moving out a bit in scale. So currently, this is how we detect exoplanets. Or it's pretty much how Kepler works. The planetary mission Kepler works. This is in fact data taken from one of the first exoplanetary detections, and what's happening is essentially you stare at the star, this orangey thing in the background. You stare at the star and you just measure the amount of light you're receiving from the star, and that's 0 on this plot on the bottom. And then what happens is, periodically, you hope, a planet goes across the surface of the star, and that blocks some of the light because planets are opaque, and so the amount of light you get from the star goes down a bit, and then when the planet stops crossing the front of the star, it comes back again and goes back to being its normal brightness. And what you can see here, that this example, the planet blocks out about 2% of the light from the star in the background, and you can use that as a robust detection of the planet. Now, what's useful about this is you can tell lots of things. you can work out, for instance, how big the planet is, because the bigger it is, the more light it blocks out. Now, that will also depend on how close it is to the star that it's transiting across. But you can work out how close it is because you can use Kepler's third law. There's a relationship between the period of the planet, which you can measure, of course, because these dips are periodic. And so you can measure what the period is. And if you know the period, you can work out how far away it is from the star that it's orbiting. Because you know the mass of the star, because you know what type it is, because you can use a HR diagram, Hertzsprung-Russell diagram. So you can work out how far the planet is from the star, how big its orbit is, and then you can work out how large that disk is on this, how large in radius that the planet is. Now, if you can combine that with another observation, which is if you've seen one of these, you can look to see the star move backwards and forwards slightly as the planet orbits it, using the Doppler shift of the spectral lines from the star. So you can actually measure how much the star moves backwards and forwards, and that allows you to work out the mass of the planet, because it's the planet that pulls the star backwards and forwards a little bit. And that will allow you to work out how massive this planet is. And if you know the mass and the radius, you can work out the density. And if you know the density, you can work out whether that's a gas giant or a rocky planet, for instance. So we can actually measure quite a lot of stuff about extrasolar planets once you make these detections. And this is the main way that the Kepler satellite actually does detections. It stares at lots and lots of stars, and it looks for little dips in the light from those stars that come periodically, and that lets you say that there's a planet there. And the reason you want it to be periodically is, of course, there are other things that could be on the surface of stars, large sunspots, for instance, which will happen on a period of the stellar rotation and not on the, and they don't stay forever. They don't stay in the same place forever, whereas a planet keeps coming back on a regular basis. So you can keep seeing it. So that's pretty much how we do extrasolar planetary detection. That's how almost all of the current detections are done. In fact, you can do this with an amateur, well, a decent amateur scope, a 12-inch or a 10-inch scope with a CCD camera attached to it, and you can make these light curves, and you can actually see these extrasolar planets for yourself if you want. One of the early ones was done on the roof of St Andrews University, for instance. So I mean, you only need 2% photometry to do this. Anyway, so that's how we detect them. The other thing that's in terms of searching for planets that are a bit Earth-like is we'd quite like liquid water. And we can work that out because, as I've just said, we can work out how far away the planet is from the star because we know its period, its orbital period. So that tells us how far away it is. And if you know the stellar type, you can work out how hot the star is. And so you can do a calculation for how hot the surface of the planet is likely to be. Because the further away from the star, the cooler the surface temperature will be of the equilibrium temperature of the surface of the planet will be. And so we can work out where that is, and we can work out what the band where we think that the surface temperature on the planet will be somewhere between 0 degrees, so frozen water, and boiling water, so somewhere between 0 and 100. It'll be narrower than that in practice, but somewhere we can work out where that is, and that we call the habitable zone or the Goldilocks zone, the region where it's not too hot and it's not too cold. And that will be further away from the star the bigger the star is. So for the sun, which is 5,800 Kelvin, you get a band that stretches around 1 astronomical unit and goes in about as far as Venus and out probably close to where Mars is. Whereas for a much smaller star, the band is narrower but much closer to the star because the star is cooler. And we can calculate where those are. So that's where the Goldilocks zone is. Which brings me to Trappist, which is the system that I wanted to talk a bit more about. So this is a real extrasolar planetary system called Trappist 1. It's the first detection from the Trappist system, which is a transiting planet detector, a dedicated transiting planet detector. And they discovered this amazing system. It's actually got 7 Earth-like planets, or Earth-size rocky planets in it. Right, so there's 7 of them in this system. So the Trappist star, the star that's inside this, is actually much smaller than the Sun. It's close to a brown dwarf. It's a little bit bigger than Jupiter in terms of size. It's a very small star. They deliberately picked that because if you have a small star, the planets that orbit it take up a bigger fraction of the disk, and therefore you're more likely to spot them. So they look deliberately at small stars to start with, and this is one of the systems they found very early on. So it's a 7-planet system. And if you're wondering how on earth are those real, are they really, here's the data. Here is the light curves for when it's been centered on when the planet transits, but I think you would agree that these are all pretty reliable. I mean, they all look like proper detections. They're not just tiny in the noise sort of detections. They're all pretty clear. And what you can see neatly is that as you go further and further out from the star, the transits take longer. The planet is moving more slowly. That's what you would expect, and they all look pretty solid detections. So that's the actual data for the actual detections of these things. So 7 planets in the same system. I mean, you can detect more than one planet because they all have different periods. Of course, it's not like they overlap with each other. You don't get one that goes to different depths. They all have different orbital periods because they're different distances from the star. In fact, the orbital periods are written down the right-hand side here, so they vary from sort of 1.5 days to something that's closer to 20 days as you go down. So that's the detection data. How do they look? Well, in terms of the Goldilocks zone, well, some of them are pretty good actually. So here along the bottom is the equilibrium temperature, so how hot it is, and up the side is of this plot is stellar mass, and you can see that this these are all other extrasolar planetary detections on this plot, but along the bottom here is Trappist. It's quite a small star. It's not much bigger than a brown dwarf, as I already said. So on this plot, the planets that are further out are on the left of this plot. So this one is the one that's closest. It's the one that's hottest. But what you can see is that Trappist D and E actually have temperatures that are sort of Earth-like. D in particular has got very Earth-like, would likely to have very Earth-like surface temperatures. And as I said, these have got masses of around a solar an Earth mass, and they're rocky. So these are rocky planets of Earth-like masses with temperatures that would allow water, essentially. And there's more than one of them in this system alone. There's 2 that would lie within the Goldilocks zone in this system. Now, before everyone gets too excited about this, it's not an ideal place for life, for instance. So one of the issues is the system's incredibly small. So here is the Trappist system to scale. So on the bottom here is Jupiter. Here's Trappist. It's only a little bit bigger than Jupiter. The Sun is much bigger. But the Trappist system actually into scale looks like this. The 7 Trappist things would fit pretty much within the orbit of Callisto. So they're like the Galilean moons, essentially. They're well within the orbit of Mercury. All of this system would fit within the orbit of Mercury. So that's a problem because if you calculate how this would happen, all these planets are likely to be tidally locked to their star. So they're a bit like the moon around the Earth. So for every orbit of this planet, it has one rotation, and so the same face faces the star all the time. So they're not likely they're likely to be pretty hostile to life for that reason, because they're tidally locked. And the other problem is the Trappist star, being a brown dwarf, is also quite active. We've already seen at least one Carrington level event on this star while we've been looking at it. So these are going to be they're so close in that they're liable to suffer from variations in their host star, essentially, as well as being tidally locked. But as an example of Earth-like objects near to, orbiting a star, this is a system where there are several of Earth-like objects. So the other interesting thing is back to resonance. They also are all in resonant orbits. So not only are they tidally locked, they also exhibit a resonance. So one of the interesting things about that is that if you convert their orbital periods and play a note each time they cross your line of sight, you can convert the system and get it to play some music. So here is this is not done by me, I hasten to add, but if you convert the system into music, it sounds like this. Hopefully this will play out through your speakers. We'll see whether that works. Hopefully that wasn't too loud. The idea is that's what happens when you have a resonance system. You make what sounds like music, because the notes are being played at regular intervals, and so that's one way of representing a resonance system, so that you can see that it's in resonance, because it actually makes what actually does to our ears sound like music. So that's actually, I think, still the longest resonant chain that we know of. There are 7 planets in a resonant chain from the inside to the outside. The outer one, I think, goes around 24 times once. The inner one goes around 24 times for every once of the outer one. They're all in different resonances as you go out, so it's a very, very interesting system. It must be incredibly unstable, but it's currently in what is a pretty stunning resonance. So just to finish up, I'll just show this slide, which shows you the future for exoplanet detection. So there are lots and lots of current satellites, current missions planned to look for exosolar planets. It's a very, very hot area within astrophysics. We're seeing lots of new planets. There are thousands of them currently known. There are more thousands are going to come along. What's shown on this plot is period along the bottom, so how long it takes for the planets to go round the star, and up the side, masses in terms of Earth masses. So what we were looking for in terms of extrasolar planets that look like Goldilocks planets, so planets that are have liquid water and a period something like the Earth, or planets around here, sort of, in a year, and Earth-like masses. And what you can see is that by the time you get into the 2030s, so sort of a decade and a half from now, we're hoping that the number of planets in that region of the diagram will expand hugely, and we'll start to see a lot of planets in that region. I mean, the different colors on here show different techniques. So what currently you see that with the planetary detections is dominated by transits. But then what will take over is microlensing detections as we move into the next decade. But there are plans for detecting hundreds of thousands of extrasolar planets over the next sort of 15 years or so, and that will mean that we'll open up a whole area of knowledge about how planets form and evolve. There's already lots of interesting things which would fill many other talks about what we know already, but it's certainly going to be an area where new researchers moving into this area are going to have a mass of new data to work with. So it's very exciting. And at that point, I'm going to wind this up and move on to questions.
Thank you, Fraser. That was a fascinating talk. For people wishing to ask questions who might be new to Zoom, you'll find a little button at the bottom of your screen, which you can click to do Q&A, and there you can type in any questions you may have.
Right, so we've got 3 questions already, haven't we? So I'll start at the top then. So how many exoplanets could be hot Jupiters? Not quite having the mass. Well, indeed, there is once you get much above the Jupiter mass, then you do get brown dwarfs. I mean, so as we just saw when I talked about Trappist, Trappist isn't much bigger than Jupiter. It's actually about 10 times more massive than Jupiter. So Jupiter is about 1,000th of the mass of the Sun, and the Trappist star is about 100th. So there's about a factor of 10 there between the two. I mean, Andy, you might be a better person to answer that top question, in fact, in terms of how close it is to actually igniting. But my belief is the numbers counts of planets sort of drops and then rises again as we go into brown dwarfs. Is that right?
Yeah, I'm not entirely sure on that as to, and I think it is a kind of, it's a very vague line which you have between sort of a hot Jupiter and a kind of a brown dwarf. So kind of quite where you draw the line between failed stars is, as I think, a very kind of, it's as much down to sort of where humans draw the line, because I think you can have some stars which last for an incredibly long time because they're just burning very, very slightly, and others which won't burn hydrogen but will burn deuterium, that kind of.
Yep. So so if we go on to the one below there, talking about whether you can detect lots. Actually, you can. I understand you can just obviously Fourier transform you can Fourier transform the luminosity curve and use that to look for periodicities, because you do indeed want to look for a periodic signal. But my understanding is you can also just do it by looking that you don't really care if there are multiple planets, because they have different periods, and so you will see the dips are a long way apart. It typically only takes a short fraction of the full orbit in order for the planet to transit. If you think about, for instance, those of you who saw Venus transiting the Sun, our Sun, a few years ago, the transit of Venus only takes a few hours, out of an orbital period, or an orbital period that's much longer, and so you're actually looking for dips, and then you can then predict. You then look to see when that comes back. So actually, you don't necessarily need to Fourier transform it. You don't have a problem with them confusing it. It's not like oscillations with different periods. It's essentially flat for a long way and then a dip, and then flat for a long way and then a dip. So you can just pull them out from the data. I think that the Trappist system itself, it's pretty obvious you could tell those apart. They have different periods because the planets are further away, and different depths. They look very different from each other. So it's you could do it the Fourier transform way, but I don't think you need to. Could I estimate the percentage of researchers worldwide researching exoplanets? It's been increasing a lot in recent times. In the UK, my understanding is it's something in the order of 30% of new postgraduates are doing exoplanets or something related to that. I mean, you could look up the numbers from the attendees at the last few SDFC summer schools for new PhD students, and see how many of those are registered doing, that had registered doing exoplanets. But my guess would be it's somewhere around a third of new PhD. Now, total researchers will be less than that, because there's a lot of inertia in the system and people stay researching what they did before. But it's certainly a rising field. So within the UK, there are 500 or so academics, and I'm not sure how many of those, probably 50 or more, are doing exoplanets directly. So at NAM a few years ago, we had a pretty strong exoplanets section. Essentially, it's one of the major sections within research worldwide, and certainly within the UK. There's several big groups. Andy, again, you might have a better idea. Exoplanet detection, you do that. Exeter's pretty hot on exoplanets.
Yeah, I mean, Exeter has quite a few sort of researchers. Again, it's kind of a bit of a mix, because you've got the from the professors down to the postdocs to the PhD students. Yeah. So I would guess we've got 20 to 30 at Exeter maybe alone. So it's a big fraction of us, but then it's probably big compared to a lot of other universities in that sense.
Yeah, I mean, in Nottingham, we don't do exoplanets, so we have 0. But yeah, I mean, certainly Leicester has a big exoplanets group. There are lots of quite large exoplanets. It's definitely a hot topic within UK astronomy. How far are we away from detecting life using spectroscopy? That was one of the key drivers behind Next Generation Space Telescope. One of the things they were trying to do. So one of the things you can try and do is do spectroscopy in occultation. So the idea is as the planet moves across the surface, you block out the background light, but some of that light comes through the atmosphere of the planet. Some of the remaining light comes through the atmosphere of the planet. So if you subtract the two, you might be able to see what is absorbed by the atmosphere of the planet. And I used to say you look for ozone, but I don't believe that's the case anymore. There are basically molecules, there are compounds that you might get in a life-bearing. If you saw ozone, that would be an obvious one, because ozone, O3, is not something that you get. It's very volatile, so you have to keep making it. So that's a key life indicator. But my understanding is they're not going to look. Ozone is not the thing they're going to look for. But the idea is there, right? You look for some compound that's made by life, and you look for it in absorption in the atmospheres of these planets as they transit. How close are we to doing it? Nowhere near with our current equipment. But given the whether it's done by NGST or not, or the next gen, or the telescope that comes after that, certainly within the next, it's one of the things that's certainly planned for next generation telescopes is to do spectroscopy to look for life in the, and the idea of how to do it is sort of obvious how you do it. It's just hard because you've got a whacking great big star and a thin atmosphere. I mean, none of the planets we currently have, I don't think, are good candidates yet. But I think my last slide indicates that planets of that type, of the type we want, are coming along. I mean, it won't be that long before well, I mean, we're getting already, but we're getting close to getting Earth-like planets orbiting Earth-like stars at Earth-like distances, and at that point, we could start doing. You could start asking that question: do they have atmospheres with signatures that would support life? We know how to do it essentially, but it's a really tricky experiment. How does your greenhouse effect affect your definition of the Goldilocks zone? That's a very good question. It does a little bit. So, for instance, the equilibrium temperature of the Earth is not above zero. It's like -18, I think, -15 degrees. It's only raised above zero because we have an atmosphere. So the atmosphere adds 30 odd degrees to the equilibrium temperature of the Earth, which makes it so that we have liquid water. So it moves an atmosphere generally moves the Goldilocks zone out a bit because it raises by the IR reflection. It raises the temperature a bit. You have to be a little bit careful because, of course, you can raise the temperature a lot if you do what Venus did. So you have to be a little bit careful with that. So it does indeed, and it's not the only thing actually that makes a difference. The albedo makes a difference too. So the equilibrium temperature varies depending on what color you paint the surface. If you paint the Earth white, snowball Earths happened early on, and they are frozen because the surface is white, and the albedo means that you reflect much more of the incoming light, so the equilibrium temperature is lower. So you can also change the Goldilocks temperature, the surface temperature, by playing with albedo too. So it's all a bit unclear. The other thing that can make a difference as well is elliptical orbits, of course, because you need to stay within the Goldilocks zone if you're going to have liquid water. You want nearly pretty circular orbits. If you wander in and out of it, you'll periodically freeze and boil, and that's not good either. So there are lots of things to consider. The basic idea is simply that there is a region around any star where, given a circular orbit and the right thickness of atmosphere, where water will be liquid on the surface, and you can do a rough calculation of where that is. But yes, the greenhouse effect or atmosphere rather than greenhouse effect will make a difference. How will our knowledge develop about the chemicals in rocky exoplanet? Well, that's a very good question. I don't really know what the answer to that one is. One of the interesting ones, one of the planets, I believe, the lowest density planet we have is very much less than water. It's something like the density of styrofoam, which is a very strange planet. Now we know this, we can measure the size, we know the density, so that will tell you whether it's rocky or not, but it won't tell you what type of rock it is. Presumably, you'll be able to tell the difference between a core and some planets could just be a core remnant, and some planets could have a thick mantle, and that would vary the density a little bit. So that would make a small difference to the size, but actually what it actually is, I mean, you're going to have to assume that it's a mantle with a differentiated core if it's big enough, presumably. I mean, the processes that sink the iron to the middle are pretty well known. So I think that's true, but direct evidence, we're not going to get any.
Well, I can actually add a little bit of an intrigue to there. There's some researchers had an actually great idea to find out about the chemical composition of rocky planets. And what they actually do is they look at white dwarfs. And with a white dwarf system, you sometimes get a bit of chaos going in towards the end of a star's life, and it causes some of the planets to break up and crash onto the surface of the white dwarf. And then you can see this chemical composition of those planets for a brief period of time on the surface of the white dwarf. Obviously, it doesn't tell you anything about any planet you discover, but it gives you some ideas of statistics of what planets are like.
Yeah. I mean, presumably, like the pulsar planets, for instance, are probably just iron cores. So, I mean, you can probably do some stuff by inference, but all you're really going to have for an individual known object is its density, which doesn't tell you a huge amount about the actual composition. I don't know, other than that, like that's sort of a destructive test, right?
Yeah,
other than
it's
that,
quite extreme to, you find, oh, that planet could have supported life.
Yeah. Every other planet. So every planet does indeed have an effect on the solar wobble. This is so when you're doing Doppler detections to work out the mass of the planets, that is indeed true, that that's not going to be flat and then a dip and then flat and then a dip. That's true, and so they're all going to be superimposed, but they all have different periods. And so you can then just decompose them into their individual, that you just get beats, like when you play notes of different frequencies, you can hear those perfectly easily. It was Bragg or somebody who said that it didn't matter how many guns fired, you could work out where they all were, because the distances were all different, and so you can decompose them because they have different periods, so that the signals are readily decomposable. If going back to one of the earlier questions, one thing you can do is, of course, just Fourier transform it, and you'll just see the different frequencies straight away. And then once you know the frequency, you can pull out the amplitudes easily. Yeah, Fourier transforms, but they've got different periods fundamentally, so it's not a problem. Good question. Are we able to show if there is enough water in other solar systems? That's a very good question. Hopefully, if we can do the absorption studies to actually look at what the atmospheric competition is, we might be able to detect compounds that include water. But it's one of the issues, because this is one of the reasons I went through the thing at the start with the Earth and the migration of Jupiter, because we think the migration of Jupiter was responsible for bringing a lot of the water into the inner solar system. Otherwise, it might have been much, much drier. And so a lot of these systems may, if they don't have that similar migration, they may be very dry, in which case that may be one of the problems for bringing water into the inner solar system. Inside the snow line, you just might not get very much volatile material. That doesn't stop you necessarily having environments where you could develop life, because the moons of the outer planets may be suitable, for instance. But it's not obvious that all solar systems, even if they have an Earth-like planet at Earth-like distances in an Earth-like star, it's not obvious that those are going to have plenty of water. And that's one of the reasons I wanted to start with that, how we think the solar system worked, because it may be that that's not how it commonly works, because it's a bit of a coincidence that before Jupiter crashes into the sun, that Saturn catches it up in this resonance, and then they move back out again. And maybe that's not that common. We don't know is the answer to that, and it's not obvious, the answer to that question. Will we be able to show? There's ways of doing it, but it's not obvious. Once Jupiter and Saturn have been close to the sun, what supplies the energy to push them away from the sun? Good question. Gravity, essentially. What's causing them to migrate is that in the disk of debris, you form essentially a tidal, like a spiral, and on the inside, it's a bit like a spiral arm in a spiral galaxy. You get like a wake that leads you and a wake that trails you in the disk, and which of those two is bigger tells you whether the planet migrates inwards or outwards. So if the inner one is pulling more, you'll migrate in one direction. If the outer one is pulling more, you'll migrate in the other direction. And it's a balance between those two. Now, in general, the net of those two things is that you migrate inwards. That's how it generally works. There are situations where a single planet migrates outwards, but generally it migrates inwards. Now, when you've got two planets, there's no arm. The arm on one side of them is broken because the other planet's in the way, and there's essentially a gap. And so the setup is slightly different. And in that setup, in the Saturn Jupiter setup, the migration is outwards. And so because the forces are pulling you outwards, the combination of the outer arms and the inner arms is such that the force makes you go out, or pulls you out, we think. And so it's exactly the same system as when a single planet migrates. There are two. It's like having two elephants pulling you in opposite directions, right? One of them slightly bigger than the other, so you get dragged in that tug of war towards the bigger elephant. And when you've got two systems, that effect is the bigger forces pull you out. When you've got one planet, generally the forces pull you in, and so it's just a competition between the two. There's no change in the physics of what's going on, really. It's just a balance between the two things, and the balance shifts when you have two planets. Yeah, it's nothing other than gravity. Can amateur astronomers make positive and meaningful contribution in detecting amateurs? Well, they did, in fact, early on. There was quite a few detections that were made by amateurs. One of the first detections was made by an undergraduate project on the roof of St Andrews University. They were looking at some stars, and they saw a transit. It was done back. But nowadays, more recently, what's happened is these Kepler, for instance, has just looked at thousands and thousands and thousands of stars, and so that's taken away that angle for the amateur community. It's a bit like what happened when supernova detection took off and got done automatically, rather than amateurs looking for supernovae at galaxies night after night after night. They still do it, but it's just been taken over by automated detection. And the same is true now for exoplanets. It's much harder to do now, just because satellites have done all the easy targets, I think. I don't know. And do you know any more?
Yeah, I was going to say, I can add a little bit on there. I know it's kind of what it's switched to is kind of more follow-up observations. So I think sometimes there's collaborations with some of the kind of professional teams who are doing the discoveries, and then the amateurs can do follow-up to then help tie down orbits and that kind of thing. And actually there's, at the BAA, there's an exoplanets division, which is part of the asteroid and remote planets section. And if you're a BAA member, you'll find details to contact that section at the back of the journal. But if you're not a member, then on the website, there's a form on the Exoplanet division web pages, which allow you to contact the director of that section.
Yep. I mean, you can certainly go and use scopes. It's certainly well within the capabilities of amateur equipment to detect extrasolar planets yourself. I mean, modern equipment will do that. I mean, it's got decent equipment, but modern equipment will do that. Many clubs would have the facilities to do that. And certainly, I mean, similar, I suppose, to the minor planet detections as well. I mean, people do follow-ups on minor planets and work out minor planetary orbits in the same way. So there's certainly opportunities there, I guess, to get involved. There is one hot Jupiter that has a very eccentric orbit around its star, almost grazing its star's atmosphere at its nearest point. How does such an eccentric orbit form? I don't know about that one. So, hot Jupiters. I didn't mention this because I know that there have been other talks in this series dealing with extraplanetary detection. I basically wanted to stick with the Goldilocks with Trappist and Earth-like planets. Hot Jupiters. So these were very strange. They were completely unexpected. So it's actually an interesting history of science topic, this. When scientists started collecting data on looking for transiting planets, in fact, they weren't looking for transiting planets, they were looking for Doppler planets. And when they were doing that, they worked out how long they would have to wait until they detected a sort of Jupiter, so something that was at 5 astronomical units and had the mass of 1,000th of the star it was orbiting. And they worked out that they'd have to wait for, you know, a few, maybe 10 years to detect them. And so they didn't bother looking at their data. They just collected data and then thought they'd go back to it. And then someone else came along and said, oh, look, I've detected all these massive planets in really Mercury-like orbits. And isn't this strange? And when they looked back in their data, they discovered they had hundreds, but they just hadn't bothered looking. And that was a bit strange because they never expected them. They never expected these essentially Jupiter-like planets very close to the star back when planets with extrasolar planets was new. And that was a bit odd. I mean, it was a bit odd because everyone had the view of the solar systems to be a bit like ours. Which all harks back to our starting point of diversity. Everyone expected things to just be what they knew. And so what they weren't expecting Jupiter's very close to their host star because they can't form there because they're well inside the snow line. So they shouldn't have all those volatiles. So you shouldn't get gas giants in Mercury, sub-Mercury orbits, or like is said here, like a grazing. There are several grazing hot Jupiters that pretty much are nearly in contact with the star they orbit. And that would be very strange. Of course, this was all before the days where we thought we knew about migration. We thought planets formed and stayed where they are and didn't move around, whereas now we know that they migrate. Or we think they migrate, and so that's been a big change in the last 20 odd years of research. So we now know that there is a population of objects which are known as hot Jupiters, which are Jupiter-like objects, gas giants, but in sub-Mercury orbits. And you can see them actually on my, if you hark back to my last slide, you can actually see a lot of these very massive objects, 300,000 times the mass of the Earth, but in orbits with orbital periods of a few days. Now, as far as I was aware, almost all of the ones of those that were detected are in circular orbits. And that's because the orbits become circularized as they migrate inwards, and they therefore they basically become tidally locked and are in circular orbits very close into the middle. So the eccentricity of almost all the ones I knew about was circular. Now you can get elliptical orbits just because it's a bit like a billiard problem. If you have more than one and they have a close encounter, it will throw them into non-circular orbits. It'll generally tend to throw one out. So if you have an encounter, I mean, occasionally you'll get orbits that are not circular. So I would suspect that you basically have what was a circularized orbit, but then you have a close encounter with another object, and that makes the orbit elliptical. So I would guess that it's just a bit like a billiard randomization thing. You tend to get messier orbits if you have some close encounter, and so I would suspect it's an interaction with a third object from a hot Jupiter in a circular orbit. How much is observation bias of massive close planets change the level of uniqueness of our solar system to be more common? I would suspect yes, it does. So the question here is that it's much easier to detect a big planet near a star. particularly a small star. So, for instance, both the Kepler things are biased towards finding close-in planets, because the closer you are to your star, the more of it you block out for the same size of object. So if you're really close, you'll block out a lot. If you're a long way away, you block out hardly anything. If you're small, you'll not block out much. If you're Jupiter, you'll block out much more. So you're biased towards detecting big planets close to the star. Yes, you are. And the answer to your question is we don't know what the bias is, because it's an unknown unknown. To quote Donald Rumsfeld, we don't know how many there are in that region because we can't detect it. So we're getting better. So one of the problems is, for instance, once you get out to say the Earth, the orbital period is a year, and so you have to wait a year for it to come back. If you get out to Jupiter, or Saturn, the orbital period's getting on for a decade, right? So nine years, and so at that point you have to wait longer than the satellite's been in orbit for it to come back again. And so there's a zone on the diagram where you can't make the detection because we haven't been looking long enough. Long period orbits just we haven't had long enough to see them come back yet, as well as them blocking out a much smaller fraction of the light. What I would suspect is, as we wait longer, we'll start to fill in that bit of the diagram. At the moment, you could ask, could we detect the Earth orbiting the Sun at some decent distance? And the answer is no, we couldn't. And so we pretty clearly detect Jupiter in some of the in the current observations, but the Earth's a real push. But the next generation of satellites, the next generation of probes, are going to be able to detect Earth-sized objects at Earth-like distances. That's what they're designed to do. So the answer to your question is, we don't know whether the Earth-like solar systems are the archetype or whether hot Jupiter-type solar systems are the archetype. We don't know the answer to that yet, but we're going to find out. Could you explain again the mechanism that causes a planet to migrate away from the sun? Well, I can try. It's a balance. So you have a disk of material, a bit like a frisbee or whatever, a bicycle wheel, and a planet forms within it, and it clears out a channel or whatever. It sweeps up the material in its orbit, but it also generates like a leading and a trailing wake within that disk, and it's a balance then between whether and those wakes pull the planet. I can't think of a good analogy. Basically, the things that excites gravitationally pull the planet. So then the question is, which is bigger? The one that's bigger will pull the planet towards it, and so it's a competition between whether the wake on the outside pulls you more than the one on the inside, and so it's a race essentially. It's a bit like a tug of war, and at the beginning, it's a balance, and sometimes it pulls you one way and sometimes it pulls you another way, and in certain situations it'll pull you out, and in other situations it pulls you in. And there is a calculations. People have made calculations as to what those criteria are for whether it makes you migrate inwards or outwards, and what we generally think is that most planets migrate inwards generally, but in the situation of the pair of planets in a resonance, that generally migrates outwards. And so before the resonance forms, the two planets individually migrate inwards, with Saturn migrating faster than Jupiter. So it catches it up. And of course, as it catches it up, its orbital period will get faster and faster, and eventually it moves in till the orbital period is in a resonance, a 3-to-2 resonance in this case. And at that point, it gets locked in that 3-to-2 resonance. And at that point, it then clears out the gap between them too, and the pair then migrate back outwards again. So it's essentially a tug of war between the forces pulling the planet in and the forces pulling the planet out. I'm not sure if I got any better there. So sometimes quoted as millimagnitude. Is this? I don't know. I'm not an observer, but I would guess it probably is.
Yeah. That's right. Thousandth of a magnitude.
Yeah. So the one I showed you that was not done in millimagnitudes, that was just done as a fraction. So it was 2% essentially the dip, and that's a reasonably big one. So most of them will be down at 1,000th, of the original.
And typically amateurs can get to 100th of a magnitude. Occasionally you can get better, but you're always chasing different kind of problems with kind of various systematic errors or random noise. Yeah.
So I mean, that was 2%, but I don't know how bright the star was. It was orbiting. Well, we could look it up. It was on the slide. It told you what that star was. It's one of the HDs. I think.
Yeah, the brighter the star, the easier it is to detect because you have the more photons. Yeah. Therefore, it makes it easier to do statistics to see a small dip.
Yeah. So, what I don't know off the top of my head is what the magnitude was of that star. I used to. It might. Anyway, I don't know. Is there any other technique for detecting life? Well, good question. Well, I guess it depends on how broad you want to go. I mean, presumably, if we heard their radio emission, that would be a good. I mean, Jazz FM would be a bit of a giveaway, and that would be a giveaway for detecting life. So you want to go really big? I mean, Fermi bubbles would be another potential giveaway. I mean, that's one suggestion for detecting life, but not on an individual solar system basis, of course. So the idea there is that an advanced enough life civilization. I mean, this is very, very far-fetched. I should hasten to add. They use a lot of the energy from. They spread out and they use they reprocess the starlight from a region within a galaxy, and that then you end up with a region of a galaxy which emits much more strongly in the infrared than the surrounding galaxy. So you end up with what's called a Fermi bubble. And people have actually looked for in large galaxy catalogs for galaxies with IR excesses, but or also other, I should stress, ways of getting IR excesses. So you could look for infrared excess. I mean, there is the Kardashev scale, of course, for energy usage, and people have looked for Kardashev 1 civilizations, Dyson swarm type things. Then there's the one cometary system which people have considered might be a Dyson swarm. It isn't, but they thought it might be. So there are these bigger ways of detecting life, but I don't know what you mean, what you were thinking, whether you were thinking, is there a way of detecting? I mean, looking for compounds in the atmosphere of the star is the way that has been proposed. But there are large programs listening to various, looking for electromagnetic emission. But that would be intelligent life. It's quite hard to detect other than as a life compound, like amoeba or single cellular life forms on other planets. I mean, you look for their byproduct essentially. I don't know whether that answers that question.
Yeah, I mean, it's hard enough trying to find life in our own solar system beyond the Earth to know where for sure. So.
Yeah, I mean, how would you? I mean, if there was life in Callisto's oceans, how would you go about? I mean, the only way to detect it would be to go there and drill through a kilometer of ice. Yeah.
I mean, and we're about 8:15, and we've got another Oh, we've just gone up to 8 questions. Shall we aim to finish around about 7:30, do you reckon?
Yeah, we could try. Yeah.
See how we get on.
Yeah.
I'll do this. I'll take the question.
How will future observations remove observational bias of massive close hot Jupiter planets, change the level of uniqueness of the solar system to be more common? Perhaps we are not so odd. I think we answered that question already. Well, so the way they'll do it is that you'll have a longer time baseline, so you'll be able to detect longer period planets, but also we talk harking back to our amateur discussion, you'll be able to detect smaller dips because you'll have better, larger equipment, and so you'll collect more photons, and that will allow you to improve your signal to noise. So both signal to noise improvements and longer timelines will push the detection, but also more stars, look at more stars. And there's a new technique called microlensing technique, which is going to come along as well, which is planned. But that's a different talk as to how other techniques will take over in the next 15 years or so. But yeah, so basically a combination of better techniques, new techniques, longer baselines, and better signal to noise all help in this area. There has been a report this week that Titan is drifting away from Saturn 100 times faster than science expected. Are you aware of this within your research of transit planets on the solar system? No, I've not heard that. I've no idea why Titan would be drifting away from Saturn. I mean, it's just a rock orbiting hundreds times faster than. I mean, the moon does move away. It's moving slowly away from the Earth, and that's due to a tidal interaction. So it's because some energy is being dissipated in essentially the relative spins of the two. So in order to conserve momentum, the distance between them has to change. So presumably it is possible for Titan to move away from Saturn because it's to be another system where there's a tidal interaction between Saturn and Titan. I've no idea how that calculation works, and I mean it could be that it's moving out at 1 inch per millennia, and now it's moving out at 10 inches per millennia or 100 inches per millennia, which is neither here nor there. I don't know the numbers, and I haven't seen that work. But it's perfectly possible it's moving. Wouldn't be surprising. The moon moves out. With all the complex conditions you described in the formation of the solar system, how is it that life-bearing planets will really exist elsewhere in the galaxy? That's a question for another talk. So sites that could bear life seem to be common. That's so sites where it's possible for life to have formed and evolved. I mean, even within our solar system, there's probably several. I mean, Mars seems perfectly reasonable early on in the solar system. We already mentioned Callisto, basically moons with ice oceans, water oceans, liquid water oceans. There's several. There seem to be several sites within the solar system where life could have developed. Whether it did or not, we don't know yet. That's one of the drivers for going to go to Mars, for instance. And that harks back to, are we all Martians? I mean, life could have evolved on Mars first within our solar system. So we don't know the answer to that either. And so it appears all the research in the last 20 odd years, 30 odd years has increased, I would say, the potential for the number of sites. I mean, 30 years ago, we really didn't know how many, whether other stars had planets, whether planets were common. I think we can say pretty surely that planets are pretty common. There are a lot of hot Jupiters, yes, but that doesn't rule out Earth-like planets. It certainly doesn't. So my guess would be Earth-like sites where life could have evolved will be pretty common in our galaxy, in the universe. That would be so. Whether those planets are life-bearing is a totally different question. I don't know the answer to that. But planets capable of sustaining life, I would be surprised if they aren't pretty common. When planets migrate, what happens to their moons? They move with them. They probably don't have moons necessarily, though. At that stage, it's not clear. That's right at the beginning where there's a debris disk. It's not obvious that they've got moons. This is pre the planetary bombardment phase. So if you think about the solar system, for instance, what I didn't mention was, for instance, like our moon was generated by, we think, by a sort of Mars-Earth collision. Not the Mars, a Mars-like planet, and the Earth reasonably late, and which is why the moon has got the moon is largely mantle. It doesn't have a very big core, and we've got a surprisingly large core for the converse reasons. And so Earth and a Mars-like object had an impact, and that formed our moon. So if they have them, they probably migrate with them. But moons like our moon, or the moons of I imagine they're late. They're late acquisitions. Rather, by late, it's still very early in the solar system, not right at this, but they don't have to be there through the migration phase. The brighter exoplanet stars I've looked up in Simbad seem to have high proper motions. Is this due to my poor limited choice of stars and just coincidence or something to be expected? I've no idea. I mean, presumably high proper motions is simply because they're close to us. I mean, basically it's easier to make detections for nearby stars, presumably. And so the nearer ones tend to have the higher proper motions. They're just brighter. We're back to the ones that are closer for the same star, it'll be a brighter magnitude. So you'll be easier to do the detection. You'll get more photons. They're just nearby, the nearby ones generally. So on average, you'd expect them to move more than the ones that are further away. They're close to us on average. That doesn't mean that the nearby ones have planets more than others. It's just that they're easier to detect the planets in. Would the fifth gas giant that was ejected from close to the solar system have stayed within the sun's? Another good question. I think that in the original Nice scenario, the fifth one is ejected. It is given escape velocity, but I think it's unclear. It's unclear. I would be surprised if it wasn't thrown out, because otherwise it would presumably be on a long scale orbit, and that seems unlikely. So I think in the original Nice scenario it becomes unbound and is ejected.
I think within the last sort of 10 years, there has been quite a big search in case there was a kind of super Earth-sized sort of planet, which I think fitted some of the models, and they really thought they were going to find it. And I think we're quite surprised when they found nothing.
Yeah, so originally that was called Planet X for Planet 10 or X if you want now. And they were looking for sort of a 20 Earth mass object. And they thought they knew where it was from some of the perturbations in presumably Neptune and Uranus's orbits. But I think that's maybe different from the Nice scenario planet. I mean,
I think there was something, it was about sort of 10 years ago when I think it was probably a similar kind of modeling. It might even been the same where I think they looked at a scenario with something in a big elliptical orbit, which would kind of go out to the Oort cloud or sort of that sort of region, and then occasionally come closer in. And they did some dedicated searches, I think, with some large sort of infrared telescopes.
Yeah. I mean, you pretty much know what the orbital dynamics are quite reasonably, because you have to move Saturn from a 3-2 resonance out to where it is. And so that pretty much gives you the energetics. And so you know the initial state and the end state of several of the bodies, and so you can probably have a good guess as to what fraction of those leave you with the fifth planet being unbound, and so you could do the calculation. I think that it's ejected. You mentioned in the talk about a gas giant being ejected. Have there been any searches for such an object? Well, there we go.
Okay, yeah.
Andy's just answered that one. What about the proposal to place a submarine into the ocean of one of Jupiter's moons to look for life? Well, yes, there have been. The problem is one of the questions there is whether it's ethical to do that, because once you drill through, you contaminate the ocean, and it's pristine because it's been covered in ice for several billion years, presumably, and so it's you'd want to somehow make sure you don't contaminate that environment, and that's quite hard to do. So you have to be. There's quite a lot of debate about that. I mean, it's a tricky thing to do. I mean, back in people have been talking about this since the 60s, presumably. I mean, back in the day, one suggestion was you simply land a sort of nuclear powered device on the surface and melt it down, and it would sort of melt through the ice. but that's pretty unethical nowadays. Be viewed as perhaps not the ideal way of doing it. I mean, it's a big task drilling through a kilometer or however many kilometers of ice it is to get into the ocean underneath. I mean, even on the Earth, there's been big debates about drilling into Lake Vostok, for instance. So I think there are ways of doing it. It wasn't really a submarine. It was basically drilling through the ice and then lowering a probe or dropping a probe through the ice, and then I mean, I guess that is a submarine if it drives around, an autonomous vehicle. But you'd want to be pretty clear that it was somehow clean, and I'm not sure we know how to do that.
Yeah, I think it's very difficult to actually make things 100% clean without any microbes or viruses. It's almost impossible. I mean, One thought I did have is when you look at pictures of Europa, you can see it looks as though the ice has cracked at times and stuff has come up. And what it might be an easier mission to go and land and have a look at some of those regions just on the surface, see if something's been brought up. That might indicate the presence of life which has died on the way up.
Yeah. Well, presumably you could find sort of single cellular sort of, if it's contaminated with amoeba or something, you wouldn't need much, and then you wouldn't be contaminating it. So that would be a potential, right? Yeah, to see. And you probably don't need very much in order to see that there's something there. I mean, the idea would be it would be something like, like the ocean vent life, living around, outlets in the ocean. Yes. I mean, there's a rocky core, so yeah. Anyway, there you go.
And I think that's the last of the questions. From David, a thought-provoking topic. It has raised a number of useful points for me. I have to leave now. Thank you so much. Well, thank you, David. I guess you've left by now, but thanks. And what I'd say is thank you very much to Professor Fraser Pierce for joining us this evening and giving us a fascinating talk. That was a very, very good, very interesting, and we had a huge number of questions there. So I see we've had about sort of 25, and we had about 130, 140 during the peak of the presentation, and held out to about sort of 60 to 70 by the end of the Q&A. So it's been a good session. I'll just briefly share my screen to show. There we go. For next week's webinar, we have a talk on the Reverend Dr. William Pearson, co-founder of the RAS, and that's by Mike Frost, the BAA Historical Section Director. So I hope many of you can join us again next week, and thank you for coming this week, and thanks once again to Fraser. Goodbye.
Goodbye.